Hello and welcome. These are the solutions to practice quiz 15. How many protons, neutrons, and electrons does an iodine 127 ion contain? So with our periodic table open, iodine is atom number 53. And so it's going to have 53 protons, one more electron, so it's going to have 54 electrons. And then the difference between 127 and 53, so 127 total protons and neutrons minus 53 protons gives us the number of neutrons, which would be 74. So answer C. Molecule has a molecular weight of 180.2 AMU. What is the mass of the molecule in grams? Okay, so the number of grams would equal 180.2 AMU. And the conversion is just there's an Avogadro's number of AMU in 1 gram. And I hope this is something that we know and understand and can use in problems like this one here. It's a very easy conversion. Gives us a very small mass in grams as we would expect for a single molecule. So 180.2 divided by 6.022 times 10 to the 23 is 2.992 times 10 to the minus 22 grams. Which reaction below yields a metal oxide and a gaseous compound? So the metal oxide, those are the calcium carbonates. So calcium carbonates would yield calcium oxide plus CO2 gas. I'd expect us to know that the carbonates do this reaction. The sodium azide reaction, it's mentioned somewhere. I probably wouldn't expect you to have that one memorized, that this would form sodium metal plus N2 gas. So probably not something I necessarily expect you to have memorized in terms of the products for the azide reaction or the NaN3. Combustion, we should be able to predict these products or the combination of N2 and H2 producing a molecular compound. So this one's B, the decomposition of calcium carbonate. How many O atoms are present in a 6.50 gram sample of CO2? So number of O atoms equal to 6.50 grams of CO2. 44.01 grams of CO2 contain 30, that doesn't help us, contains 1 mole. So 44 grams of CO2 is 1 mole of CO2. So we're going to go grams to moles. 1 mole of CO2 contains an Avogadro's number. If I can write 6.022 times 10 to the 23 CO2 molecules. And then 1 CO2 molecule contains 2 O atoms. So 2 O atoms on each. So 6.5 divided by 44.01 times 6.022 times 10 to the 23 times 2 gives me 1.78 times 10 to the 23 atoms. Balancing the reaction and summing up. Okay, so we're going to have 7 CO2s, we're going to have 8 waters, so that's a total of 14 plus 8 oxygens for a total of 22. And so 22 would take 11 O2, so 1 plus, sum up the coefficients all together, so just 1 plus 11 plus 7 plus 8. Just a simple balancing question, so that's 12, 19, and 27. What is the mass? Okay, what is the mass of a 0.568 mole sample of barium sulfate in grams? Okay, so number of grams of barium sulfate will be equal to, we're going to start with the moles. And then 1 mole of barium sulfate. Let's look at barium on our periodic table. Where's my useful info? So barium's molar mass is 137.3 plus 32.06 for sulfur, 16 times 4 for the oxygens. That's 233.4 grams. So 0.568 times 233.4, 132.6 grams running to 3 sig figs, so that's 133 grams. Moving on. Number 7. Formula of perchlorate ion. So we just have to remember that chlorate is this, so the per is that. So it's ClO4 minus. What is the name of H3PO3. So the way I look at this is, I look at this ion here and say, okay, that's PO3, 3 minus. That's why it takes 3 H pluses to neutralize it in the acid form. So if PO3, 3 minus is phosphite, the ites become OUS in their acid form. So this should be phosphorus. This is phosphite, so this should be phosphorus acid, C. Chromium 3 carbonate is chromium 3 plus, carbonate CO3 2 minus, so it's Cr2, CO3 3. D. Propanol. Propane is C3H8, so propanol will be C3H7, drop in an H, replacing with OH is C3H7OH. Sometimes we do write this as C3H8O, but we wouldn't have that extra H if we wrote it like B, so B is wrong, C is wrong, D is wrong. Those are butanols that C and D are getting at, but A would be the right answer for propanol. Compound is known to have a formula of XO3, where X is an unknown element. If the compound is comprised of 60.0% by mass of oxygen, what is the formula of the compound? Okay, so with this problem here is trying to get us to figure out is what the X is. Now we had a few possibilities. You could just figure out the atomic weights of each of these and see which one has 60% by O. I think that's a longer way. That's not really using a whole lot of strategy per se, but what you might think is if I do 3 times 16 divided by the formula weight of this compound times 100%, that should equal 60.0%. So I can get the formula weight of the compound by simply taking 3, that's 3 times 16, so it's the 3 oxygens on each of the compounds. So do 3 times 16 AMU, and let's divide that by 0.6, so let's get rid of our 100% and make this 0.60. So we just take our formula weight is equal to 3 times 16 AMU, 16.00 AMU if you're being careful, divide by 0.600, and so that will be 80.00 AMU. And then we can look here and see, okay, if I take 3 times 16 is 48, that'll leave us with the formula weight here being about 32 AMU for the metal, or not the metal, for the other element. Then we can go look and see that sulfur has a mass of about 32.0. So this should be SO3. Okay, so you can solve it a variety of ways, but here I'm just saying, okay, I can use what the percent O means. The percent O is 3 times O. If I want to know about the formula, divide by the formula weight is 60%. I can solve for the formula weight. I get the formula weight, subtract the O's, figure out the mass of the other element, of the X, if you will. So the X molar mass is 32.00 AMU. Then I go look and see sulfur is closest to that. Last problem here is an empirical and molecular formula one. We showed this in class where, you use a mass ratio that you know to be true, 87.7 grams of carbon to 12.3 grams of hydrogen. Solve for the number of moles, get the simplest whole number ratio, get an empirical formula, divide that into here for its mass, yada yada. You can try that approach. The alternate approach is, what if you just take the fraction that's carbon times 164.3 AMU. So the total mass of our carbon atoms in this compound, and one of the compounds would be 164.3, would be 144.09. And then the mass of each carbon is 12.01 AMU. So this is the mass of just the carbon mass in AMU. And this is the mass per carbon atom. So this tells us our formula has 12 carbons in it. So we have 12 C atoms in our formula. And then if we do the 0.123 times 164.3, so if we do this for the H as well, then I get 20.2 divided by 1.008 gives me 20 for the H. So we got 20 H atoms. So it should be C12H20. So you can also go to grams here, use a gram ratio, get a mole ratio, get the simple whole number ratio, get your empirical mass, divide that into the molecular weight. That works as well. So solve these problems however you can. Use strategy, think your way through the problems. Well, that's not all for today. There's one more page. Okay, so 13, I don't know why I made this quiz so long. 13, naphthalene reacts with oxygen to form CO2 and water. How much O2 is required to for the complete combustion of 1 mole of C10H8? Okay, so I'm going to write C10H8 plus O2 goes to 10 CO2 plus 4 H2O. That's going to take 10 plus 2, so that's 12 O2s that are required. So how much O2 is required for the complete combustion of a mole of C10H8? The answer would be 12 moles. Diagram shown. 12 open spheres represent H2. The 5 solid spheres represent N2. When the molecules in the box react to form the maximum amount of ammonia, which reactant is the limiting reactant, and how many molecules of NH3 can be formed? Okay, so these are the N2s, these are the H2s, so I'm going to take 3 of these. The key is that we're making NH3, so I'm going to get 2 NH3s out, so I get NH3, so I get, if I'm maybe tracking my NH3 count, we got 2 NH3s formed, we've lost these, we've now made 2 NH3s. We do it again, we've lost these, we've now made 2 more NH3s. Do it again. Make 2 more NH3s. And then we're starting to run out. Looks like I have 3 more H's left, so I can make another 2 NH3s. So I get a total of 8 NH3s that are made. And I'm left behind with 1 of the N2s. So the limiting reactant here, the one that was consumed, is H2. So H2 is my limiting reactant, N2 is my excess reactant. 1 N2 remains. All the NH3 consumed, and I get 8 molecules of the NH3. Okay, well, the particle diagram like this probably makes sense to just lasso and think about the diagram, solve the problem that way. You could also have approached this by writing the reaction of N2. And you have to know to balance it, but it's 3H2 goes to 2NH3. So just like basically what we wrote out for every 1 of these, 3 of these, we get 2 of those, like we're lassoing out here. And so you can think of your 12 H2s and 5 N2s and sort of think, do we have a 3-to-1 ratio of H2? We have less than that. So that means that all the H2 should be reacted, go down to 0. This is minus 3x. So x is equal to 4. So we're losing 4 here, leaving behind 1 N2. So you can think through a BCA chart as well for this problem, or the particle diagram. Key is do it some way that's correct, get the right answer, and move on. Iron oxide reacts with CO at high temperatures according to the reaction. If 6.5 grams of iron oxide yields 3.85 grams of iron, what is the percent yield of the reaction? Okay, so we're told here we have an excess of carbon monoxide, so this isn't a limiting reactant problem. We know that iron oxide is what's limiting our reaction, not the CO. So the number of grams, well, the thing here, we want a percent yield. So the percent yield is the actual over the theoretical times 100%. So we need this theoretical yield here. So the number of grams of Fe2O3, our theoretical yield, would be equal to taking the 6.50 grams of Fe2O3, going to moles of Fe2O3. We're told the molar mass up here, so we'll have to calculate. So 159.7 grams per mole of Fe2O3. It's 1 to 2, so 1 mole of Fe2O3 produces 2 moles of Fe. A mole of iron has a mass of 55.85 grams. So we'll do 6.5 divided by 159.7 times 2 times 55.85 gives me a theoretical yield of 4.55 grams. And then we are going to take 3.85, divide by 4.55. Actual yield 3.85, divide by the theoretical yield 4.55. That's 84.6% yield. So we'll go with D. Aspirin is produced by this reaction below. It's balanced at 1 to 1, so it's not a balancing question. What mass of the one do you need to react with an excess of the other? So how much mass of this do we need with an excess of the other do we need to react to produce a kilogram of aspirin? So we want a kilogram of aspirin, which is this, but the yield's only 71%. So percent yield, again, is the actual over the theoretical yield we get from the stoichiometry times 100%. So we actually want a kilogram. This is kind of like saying if you actually want to make $100 a week, you need to factor in that you have to pay taxes. So it's kind of like saying, well, if you want $100 a week, you need to figure out what your tax rate is so you can figure out how much you really need to make so that you're left with $100 at the end of the day. So maybe you need to make $125, then you pay your taxes, you're left with $100. And then maybe your question is, well, how many hours do I have to work to get there? So then it's like $125 divided by how much you get paid an hour. That's kind of the exact problem that we're looking at here. We're saying we need to shoot for a higher quantity, and how much is defined by the percent yield. So imagine you want $1,000 if you want a kilogram, and your yield's 71%. Then what you need to do is take the kilogram that you want, divide by 0.71, and shoot for 1.41 kilograms. So the analogy, if you only get to keep 71% of your money, then you need to make, $1,400 a month so that you can keep 1,000 of it. That's sort of the analogy here. Okay, and so we need to try to make 1.41 kilograms of aspirin. So the number of grams, let's call this A and this C. So the aspirin we're trying to make is C. So we want to know the number of grams of A it takes to make the number of grams of C. So we want 1.41 kilograms of C. Then we're going to use the molar mass of C. And so that's C9H8O4. So 9 times 12.01 plus 1.008 times 8 plus 16 times 4. So that's 180.2 grams, but let's call that 0.182 kilograms per mole of C. Let's get rid of that point there. And then it's 1 to 1, so 1 mole of C is produced by the reaction 1 mole of A. And then 1 mole of A has a molar mass of 7 times 12.01 plus 6 times 1.008 plus 16 times 3. So that's 138 grams, so 0.1381 kilograms, because we want to know the kilograms here. So we take the 1.41 kilograms we're trying to shoot for, divide by the molar mass. We just threw it in a kilograms, so we don't have to do a kilogram to gram and then another conversion back later. So this just saves us a couple steps. And then we just multiply by, or like if we stop calculating there, it says 7.82 moles of C are what we're trying to make. In terms of kilograms of our reactant, it's going to take 1.08 kilograms of the other reactant to 2 sig figs would be 1.1 kilograms. So when we complete this problem this round, so 1.1 kilograms. So this is saying if we mix 1.1 kilograms of A with an excess of the other reactant, we should produce 1.41 kilograms of C, but the yield's only 71%. Do 1.41 times 0.71 as a check. We get a kilogram out as a result. So weird problem. This is like a problem-solving problem. Don't dwell on this one a whole heck of a lot. Just try to think through how you can use the simple ideas of percent yield and stoichiometry to solve a problem like this last one. All right, that's all for the solutions here.